Welcome to The Explainer. Today, we're diving into a concept that honestly shapes everything. I'm talking about the entire cosmos, all the way down to the device you're holding right now. It's all about this incredible idea that the most important things in the universe didn't happen because of perfect patterns, but because those patterns were spectacularly broken.
I mean, just look around you. Our world is absolutely full of symmetry. Think about a butterfly's wings or the repeating arches in a grand building. We're just naturally drawn to it. It gives us this feeling of harmony, of order, of perfection, right?
But what if I told you that in physics, perfect symmetry is actually, well, kind of boring? The real story, the one that gave us galaxies, stars, and even us, it all kicks off the moment that perfect balance gets shattered. This is the whole idea behind spontaneous symmetry breaking.
All right, so here's our game plan. We're going to start with why we love patterns so much, then see what happens when they spontaneously break. From there, we'll see how this single idea literally forged our universe and even the technology we use every day.
Okay, so first things first, we have to get our heads around a really crucial distinction here. In physics, there's a huge difference between the symmetry of the rules that govern everything and the symmetry of the actual thing you end up with. Think of it like this. The laws of physics themselves, stuff like gravity, they don't have a favorite direction. They are perfectly symmetrical. But the things those laws create, a tree, a person, a whole planet, they're almost never perfectly symmetrical. The rules are pristine and perfect, but the outcome? It's messy. And that messiness, that is where all the good stuff happens. So how does this actually happen? How does a system just break? Let's use a couple of really simple analogies to make this idea click. Picture this. You're trying to balance a super sharp pencil perfectly on its tip. The laws of gravity are pulling straight down, totally symmetrical. That balanced state is as symmetrical as it gets. But it's also ridiculously unstable. The tiniest little wobble, a breath of air, and it's going down. And here's the key. It has to pick a direction to fall, shattering that perfect rotational symmetry it had a second before. Or, how about this one? Imagine placing a ping pong ball right on the very peak of a sombrero. Again, that's the most symmetrical spot it can be. But it's not stable, right? That ball is going to spontaneously roll down into the brim. It'll land in some random spot, breaking the symmetry of its starting point. But now, it's in a much more stable, lower energy state. And that is the heart of it all. It's spontaneous. The laws of physics didn't change one bit. They're still perfectly symmetrical. The system itself, all on its own, just chose a less symmetrical but way more stable way of existing. Okay, so pencils and sombreros, that's one thing. But now let's scale this idea up, way up. Let's talk about how this explains the very structure of our entire universe. This is where it gets wild. In the first tiny fractions of a second after the Big Bang, the universe was this unbelievably hot, dense soup. All the fundamental forces we know, gravity, electromagnetism, the nuclear forces, they were all mashed together into one single, perfectly symmetrical superforce. But as the universe expanded and cooled, it went through these phase transitions, kind of like steam condensing to water, where that perfect symmetry shattered, and the forces split off one by one. And the agent of this incredible change? The one and only Higgs field. As the universe cooled, the Higgs field basically settled down from an unstable state into a new, lower energy one. That one transition broke what's called the electroweak symmetry, and in doing so, boom, it gave fundamental particles the property we call mass. We often visualize this with the famous Mexican hat potential, which is really just our sombrero analogy on a cosmic level. At super high energy, the universe is like the ball at the symmetrical, unstable peak. As it cooled, it rolled down into the stable brim. That single event, that cosmic fall from grace, is why we have distinct forces and why anything has mass at all. But look, this isn't just some ancient history lesson about the Big Bang. This principle of breaking symmetry is fundamental to the technology we build and use every single day. It might sound a little weird, but perfect symmetry is the enemy of information. Think about it. If I show you a picket fence where every single picket is perfectly white, well, it's predictable. It contains no information. But the moment we break that symmetry by painting some pickets blue, suddenly that pattern can carry a message. We can say white is a 0, blue is a 1, and we've just created the basis of all digital data. Or get this, piezoelectricity. That's the amazing property some materials have to generate an electric current when you squeeze them. It's used in everything from quartz watches to high-tech sensors. And it's only possible because the crystal structure of the material is inherently asymmetrical. A perfectly symmetrical crystal just wouldn't do it. We literally have to engineer broken symmetry to make our world work. So far, we've kind of imagined symmetry breaking happening all at once, nice and evenly. But what happens in the chaos of the early universe when different regions were so far apart they couldn't even communicate with each other?
Well, as the universe cooled, different patches of space would have broken their symmetry all on their own, in totally random ways. The best analogy is a lake freezing over. You get different patches of ice forming separately. Where those patches meet, the crystal patterns don't line up perfectly. You get cracks. The universe did the same thing, and those cracks are what we call topological defects, these massive, ancient flaws in spacetime, like cosmic strings or domain walls, left over from when the universe froze.
Okay, let's pull all of this together because the big takeaway here is really, really profound.
It's simple, really. Without spontaneous symmetry breaking, the universe would have just stayed a hot, uniform, featureless soup forever. The perfect symmetry would have meant no distinct forces, no particles with mass, no structure, no galaxies, no stars, and definitely no life. It is the act of breaking that initial perfection that allows for all the incredible complexity we see all around us.
There's this quote that just nails it. A perfectly symmetrical state is static. It's predictable. It has no story to tell. It's only by breaking that symmetry that the universe could begin to write its own epic story.
And that leaves us with this incredible final thought. We exist because a series of perfect patterns were broken. So it makes you wonder, doesn't it? What other deeper symmetries might exist in the laws of physics that we haven't even seen yet? And what new, unimaginable realities might pop into existence from the next beautiful crack in the pattern?